Now, continuing with our previous ways of developing Heisenberg's uncertainty principle, here we will try to understand this description of Heisenberg's uncertainty principle by a hypothetical experiment, a hypothetical gamma ray, using a gamma ray microscope to achieve this Heisenberg's uncertainty principle. And this method was suggested by Bohr, but it was fully developed by Heisenberg himself. And what is this all hypothetical idea about? Is that that we have an electron. Let us assume that electron is here at this point, and let me call this point as O. This is an electron, and lambda is the wavelength of the gamma ray that we are using here. So lambda is the wavelength. It's the wavelength of gamma ray photon. So gamma ray photon. And what we have is that that this gamma ray they enter into the vertical angle of a cone of rays that enter the microscope's objective from the object. Now, so we want to. The point is that we have an electron here, and we have a microscope. Okay, we have a microscope, a gamma ray microscope. So suppose this is a microscope, right? And so this is a microscope, and here is an electron. And this microscope has the resolving power, and that resolving power of this microscope is given by delta x, and that delta x is lambda by 2 sine alpha. Now, what's this alpha? Alpha is the angle. Alpha is the angle. It's a semi-vertical angle at the cone of the rays that enters this microscope. So what is this delta x here? This is basically the shortest distance. This delta x is the shortest distance between 2 points in the field of view. This delta x is the shortest distance in the field of view. Within this distance, the electron can be seen. So that's what it means here, the field of view. Okay, so if I have to translate it in other words, if the position of electron, which is at O, if its position changes by an amount equal to or less than this delta x, the microscope will not be able to detect it. It will not be able to detect this electron. Or I should say the uncertainty in the measurement of the position of the electron is given by this delta x that we proposed for the resolving power of this gamma ray microscope. Now, the electron that we have here, it is seen by the gamma radiation scattered by it into the microscope. So during this scattering, so you have a gamma ray. Let us assume that there is a gamma ray photon, and this gamma ray photon, it scatters it into the microscope. And during this scattering, the electron will recoil. Okay, it will recoil, and there will be a change in its momentum. The momentum of electron is going to change. Or I should say, this change may be this change may be as small as possible when I'll consider a single gamma ray photon incident on it along this axis, along this x-axis. Right? So a scattered photon of lambda that will enter the objective anywhere between these two lines. And if I assume this is A, this OA, and this is OB. So the scattered photon can enter into the microscope anywhere between this OA and OB. And the momentum of this scattered photon that we will have, that momentum will be h by lambda. Right. Now if it enters the objective lens, if the photon enters this objective lens along this OA, its component along x-axis will be what? It will be h by lambda sine alpha. Because here we will have the cosine component, and here we will have sine component. So the momentum that will be imparted to the electron, so I should write here momentum imparted to electron. That will be what? That will be h by lambda dash minus h by lambda sine alpha. Now, what is this lambda dash? This lambda dash is the wavelength of the gamma ray photon, the original wavelength, the wavelength of the gamma ray photon before scattering. Right? So now, if the scattered photon enters the microscope along this OB, then its component along the x-axis will be in this direction. Right? So in that case, the component along the x-axis will be minus h by lambda sine alpha. So in this case, momentum imparted to the electron along x direction, so momentum imparted to electron in case of OB, here in case of OA, that will be, what will be that? That will be h by lambda dash minus times minus h by lambda sine alpha. So this minus will become plus. So what we have resolved the components, and by resolving the components, we have tried to calculate the momentum imparted to the electron along O and the momentum imparted to the electron along OB. Right? So the momentum given to the electron can therefore have any value. It can have any value between those given by this equation and this equation. So there is a possibility of any value of momentum that's given to the electron. So therefore, so the uncertainty or the error involved in the measurement of momentum of the electron should be given by the difference of these two momentas that have been evaluated by imparting it on the electron. So what should I expect from here is the error. What should I expect from here is the uncertainty. And what will be that? That will be delta px. And what will be that delta px? That will be that will be uh, h by h by lambda dash, okay, then plus h by lambda sine alpha, right? Then minus h by lambda dash minus h by lambda sine of alpha. Clear? So we are going to have the cancellation between these two. So I will have the uncertainty in the measurement of momentum equal to this minus minus will make it plus. So this will be 2h by lambda sine alpha. So this will give me the measurement. This will give me the uncertainty in the measurement of the momentum of this electron along x-axis. Therefore, I can say I have already have the uncertainty for the measurement of its position in terms of its resolving power. So I can multiply the two to get the result. So if I call this as equation A and this is my equation B, on multiplying them, I'll get delta x, delta px is equal to, this is lambda by 2 sine alpha times this is 2h sine alpha by lambda. This lambda and lambda will go, this sine alpha will go, this 2 will go. So what we will get is the Heisenberg's uncertainty principle. Delta p delta x is equal to what? Is equal to the Planck's constant. However, I said it many a times in the past videos that the more rigorous treatment would give us this delta x times delta px greater or equal to h cross by 2. Now the point is that so if we rigorously do it, then we'll have delta x, delta px equal to h cross by 2. Now, the uncertainty principle gives us certainly the minimum absolute uncertainty in the measurement of these conjugate physical quantities like xpx is there, ypy is there, zpz is there, or energy time is there, angular momentum and angle is there. The actual uncertainties are much more. They are much large, and they certainly include contributions on account of errors due to the measuring instruments. So the things that we are achieving here are ideal. So when you are going to incorporate actual instrumental involvement, these uncertainties are going to increase to the large extent. The uncertainty principle is applicable to all objects. That's for sure. But its consequences are significant only for such minute particles, that minute objects which are microscopic in nature, like electrons, protons, neutrons, atoms, even molecules. Because in the case of macroscopic, if we talk about macroscopic objects like marble, the ball, anything that's macroscopic. I'm sorry, that's macroscopic. That's big. That's large. In those cases, I mean, their products exceed. If we take delta, if we take the product of delta x, delta px for a large object, what happens in that case is that these products they exceed the value of this Planck's constant h by many orders of magnitude. Thus due to the smallness of this Planck's constant, the uncertainty principle becomes meaningless for the measurements that the measurements that we have for macroscopic objects. But for microscopic objects, certainly it has the consequences. It has that intrinsic negativity that's involved uh, in the measurement to these microscopic particles. So even if your external errors are zero, if you boil down all the errors to zero, the system will intrinsically dupe us. It will not exactly give us the measure of the product of position and momentum of this microscopic particle.